Okay, guys, this is about as early as I can start. So I tried for 7:30, but we're here now. Okay, so I just need to pull in an image. If I can set that up down here, that would be great. Can everyone hear me? I don't know if you can hear me, so let me know if you can hear me. Okay, great. Hi, Jon Soderberg, Charlie, Stuart, hi, Nicholas, Caffarelli, good to see you here. Hi, Lucas, hi, Jason, hi, Artifact. Hi, David, hi, Austin. Okay, so where are you all at? Let everyone in the chat know where you're all at, and I'm just going to set up a different frame here, quick. UK, USA, Canada, Washington State. Fantastic, excellent. Okay, so on your screen, hopefully, you will be seeing this slide from the presentation that I shared in the newsletter at remoteview.icu. And I recorded this on, I think, October the 12th, was it? I don't know. I think it was October the 12th, 2018 at the Russian Ball Lightning and Cold Nuclear Transmutation presentation. And I had sat on this for quite a while until I realized the important, not sat on it, I published it pretty much immediately, but I didn't bother translating the slide for a long time. And it was when I was looking at the first Vega experiments, I thought, okay, these are actually making ball lightning, and this could be very important. And it got me thinking about what I was seeing with this particular slide. So what I've done is actually, I finished it about 10 minutes ago, but basically I've got so much that I wanted to get out. And when I saw, I don't know if you recall, but the coil of tungsten wire being cut a month and a half or 2 months ago, whenever it was, a long time ago now, in Lena terms, I noticed that it was cutting on the sort of double layer area, this sort of fuzzy layer to the solid boundary, and it was attaching on either one of the sides of that, and it led me to believe something that I'd been moving towards for a long time, that this was coherent matter, and in this particular zone, or a very finite area of it. And I thought we could do something very, very interesting there. And so basically, it made me think back to what I saw in this slide. Now, I'm going to translate this for you very quickly. I'm going to change the image here. And I'll just copy him, and I'll dump him here. So basically, this is low threshold microwave ball discharge. Okay, and this is essentially, as far as I'm concerned, what we have been seeing in our Vega experiments by Henk, and David's also been working in that direction. He's nearly got up to speed with his experiments, but Henk has been able to take on board a wide range of ideas, and he's a fantastic free thinker as well, and he's bringing his own intuition, and it was his actual inspiration that started these series of experiments going. So thank you to Henk, and thank you for David, who's getting up to speed, and it's just brilliant to see this happening, and I do believe that in the coming days we may see a replication of the valley, the Vega Valley, that we've been looking at a lot of in the last few weeks. By Dave, and also by Henk. Henk has got some brass plates in his current reactor, and what we've done differently in there is now, okay, so it's not a replication because we've changed something, but if we see the same tracks, at least the tracks are a replication. But what we've done is I asked him to put some potassium hydroxide in there. The reason being is that I believe that potassium, being the second most, potassium 40, which is 0.02%, I think, of potassium, natural potassium that's running through your veins right now, that is potassium 40. And potassium 40 is the second most unstable isotope in our planet, and probably near universe. And what I mean by that is that uranium-235 is the uranium-238. Uranium-235 is the most unstable, and that has about a half-life of about 0.3 the age of the universe. And potassium-40 has a half-life of about 0.9 the age of the universe. Okay, now in terms of beta isotopes, these actually still exist because they have a long enough half-life to be around for a long time, but short enough half-life so that you can observe their decay in a reasonable time frame. And so anyway, often if you are measuring background radiation, you have this 1.331 megaelectron volt peak with a sort of roll-off and that's coming from things in your concrete, for instance, in your house. So like if you get your Geiger counter and put it against there. So essentially the reason I'm asking for the potassium to be put into the reactor, and the reason I asked in a couple of the experiments we actually coated the tungsten wire or whatever with potassium hydroxide, is potassium hydroxide has three things. Oxygen, which I'll get onto in another presentation as to why that's so important. But hydrogen, so if you break down your potassium hydroxide, you have hydrogen, which is great for Lena, oxygen, and I'll come on to that later, and potassium. And if the potassium is triggered by a coherent matter state that creates something that is akin to cold neutrino clusters or cold neutrinos, according to Space Earth Human and the work of Alexander Parkhomov, are able, because there are microns to millimeters in scale, they're the size that he studied, they can actually interact with trillions of atoms at the same time. And so while it is statistically very unlikely for a neutrino to trigger an inverse beta decay, it's interacting with trillions of atoms at the same time. And then you have this extremely high density of these cold neutrinos in this cluster. And so then if you are able to trigger a beta isotope like potassium 40, that emits a 1.331 megaelectron volt beta particle, and that beta particle, not only can that stimulate activity in the reactor, it has so much energy that it can cause like Townsend avalanche of production of beta particles or free electrons. And this then, as you know from Ken Shoulder's work, the EVO likes to feed on electrons, and so that's how you energize them, and that's how you scale them up. And so something in there like potassium 40 is one thing that you can put in. Now, I have suggested another thing, which I will go and get the reference for right now, and you can do this if I can find my mouse. That is... no, it's not that. And I've mentioned this before with regard to other uses. So okay, so I'm going to see if I can get this window so that I can switch to it maybe. Let me see. Desktop app window. Yes, okay. Okay, so what I'm talking about is Krypton 85, and I've talked about this, and as far as I understand it, when you fission uranium-235, fissile material, for every 100 atoms, you get 3 atoms of Krypton 85. Now, this was such a concern to the first person that wasn't public, unlike Pons and Fleischmann, but that did this in the 1950s, called Ivan Filimonenko. He created a palladium and deuterium hot water boiling reactor. And he then found all kinds of other things, like that there was an emission of radiation, and the emission of radiation changed radioactive half-lives. Anyway, the point being is that he started to complain. I think it's this guy. He complained vociferously about the emission of Krypton 85 from both nuclear reactors and the production of nuclear weapons. And essentially, they were coming out of these RBMK reactors, which were very good at breeding the plutonium and so forth. But anyway, that put being aside, he was very concerned about krypton. It's a very heavy gas. It lies around the area of where organic life exists. And it is extremely, well, it has a very much lower half-life. So it has a half-life, if you look there, of 10.56 years. So it's sort of around about that of tritium. Okay, and the decay, if you look at it, is 0.687 MeV, so 687 kiloelectron volts, and it has another beta decay of that. Now, Krypton 85, therefore, if you put it into your reactor, would firstly, it's a poison to the biosphere. Now, actually, I think it's I think there's a French gas producer, and you can buy canisters of Krypton 85 for research purposes. And this is a little known fact, and I think I mentioned this when I mentioned using Krypton 85 before. You can actually find car headlights, I understand, that have Krypton 85 in them. Now, the reason is one of the ways you can detect that there is attempts to produce nuclear weapons, as in trying to produce the what do you call it, the plutonium, is that those reactors, they give off Krypton 85, and when you're doing a lot of this, it actually changes the electrical conductivity of the atmosphere, so much so that you get a lot of lightning, and so there's different ways of enhancing the amount of ionization that is producing electrons or ion electron pairs, and it was ion electron pairs that was being used by Winston Bostick to create what he eventually named plasmoids. And so he was creating these ion electron pairs, and so you're getting these free electrons. So Krypton is able to free electrons. The beta particle is 687 kiloelectron volts, and not only that, let me go back to that. The beauty of this thing is that if you are saying, and if we look at our brass plates that's in the current Vega experiment, and we find that the potassium-40 has decayed into calcium, okay, what I call Dec alpha, because it's the heaviest nuclide that's just made of pure alpha particles, Dec alpha. calcium 40. If we find that there's calcium 40 there where there basically shouldn't be, then we have done some transmutation potentially from the potassium into the calcium. Not only that, obviously there's potassium 39, which is most of it, and I've discussed how potassium 39 can basically be transmuted also into calcium, but it's a different mechanism. Anyway, the point about what I'm saying here is that if we can establish that something with the half-life of 0.9 of the length of the universe can be stimulated to go into inverse beta decay via ball lightning, via this macro Evo cluster, or itonic cluster, as Takaaki Matsumoto said, then why would Krypton 85 be less susceptible? I don't think it would, because it only takes 10.756 years. Now, actually, if we look at Cobalt 60, Cobalt 60 was a nuclide that's produced when you get neutrons in a nuclear reactor interacting with the steel of the reactor, and that produces Cobalt 60, and Cobalt 60 is used to irradiate, for instance, what do we call it? Fruit and vegetables, so that everything that's, everything that could multiply in your apple, for instance, is basically dead, and so the fruit and vegetables has a lot longer half-life, but it's basically dead food, and it's dead in many ways. Personally, if bugs don't like eating food, I don't really want to eat it either. Anyway, Krypton 85. So if I go to Cobalt, can I say 60? Is it going to give me something? No, I'm just going to try Cobalt 60. Cobalt 60. Okay. Now, see, Cobalt 60 has a 5.2713 year half-life. Now, Cobalt 60 was the atom or nuclei of choice for the experiments of Alexander Parkhomov, and it's unlike tritium. It's more unstable, but unlike tritium, it's not a gas, so you can have a high density in a small space. So he could make a 1 millimeter by 1 millimeter target and use a sort of pan lid to reflect the natural flux of what he called at the time, when he was first doing the experiments, N radiation onto the Cobalt 60. And he proved that over the annual cycle, and also with some lensing of celestial bodies of large suns like Betelgeuse, you could get changes in the rate of decay of Cobalt 60. And so this is like a measurable difference, but he's just using the flux from the cosmos, which is being lensed from a 22 centimeter dish down and partially reflected, that is, it's not totally reflected, partially reflected onto a 1 millimeter target. Okay, and that's a different situation to technologically producing these by causing over 1,000 degree kinetic interactions between electrons and electrons, electrons and ions, or nuclei. And these are, if they're smashing together over 1,000 degrees, he calculates that this is sufficient temperature to kinetically produce cold neutrinos. These are very slow neutrinos. They don't go very much distance, and so they can maybe condense, as has been observed apparently by Shishkin and his team in this black sort of strange radiation, and that could potentially interact with the material on a much faster basis. So if you get to the point of producing these things, and then they are interacting with beta isotopes, the more unstable the isotope and the denser it is, the vastly more likely it is to occur. And you only need a little bit of it before you've effectively got an accelerator. Now, Cobalt-60, if you look at this here, its beta decay is 3.17. However, it also produces gamma. So we don't really want to do that. That's gamma, like naturally it's producing gamma, but the beta decay is not as energetic. Whereas if we go back to our potassium 40, potassium 40? I didn't mean potassium 40, I mean Krypton 85. Krypton 85, here we go. Krypton 85. You get this beautiful 687 keV beta, or 173 keV beta, and there's no gamma ray, so it's much better in my view. And the second thing is that it decays to rubidium 85. Now the beauty of rubidium is it's almost the lowest work function material there is. So let's go to rubidium as a atom. So if we go to rubidium, let's go to P table. Okay, P table here. And in the P table, let's crank. It's not going to get any bigger, so there's no point stretching it out. If you go to the P table and we look at rubidium down there. Now they've changed this, haven't they? What have they done? Where's the properties? Properties. Ionization. There you go. Look at that. There's essentially rubidium is 403 and cesium is 375 and 380 for francium. So essentially, rubidium is the third most susceptible to ionization. So the product of your waste product from your nuclear reactor is a gas. So it is in the environment which could allow for easy ionization. If itself, it's a heavy nuclei, being krypton, so it's very good at enabling evo formation. You want a heavy gas and a light gas, so ideally you would want xenon, but krypton's pretty good too. So krypton is a good constructor of evos as a balancing agent against the hydrogen here. And look how hard you have to work to ionize hydrogen. It's 1312. That's quite a lot of effort you have to put in. It's one of the highest, in fact. Whereas krypton's comparable at 1350. But if you've created your exotic vacuum objects and the cold neutrinos are able to trigger the Krypton 85 to decay to rubidium 85, you get high energy beta, which assists in ionizing and making nascent hydrogen or atomic hydrogen. And your product is something that it can produce secondary electrons, the rubidium 85, when the high energy 600 or whatever keV beta comes out of your krypton, having been inverse beta decay stimulated, it will hit the product of rubidium, and that will extremely easily give up electrons. So, for me, I think this is worth a crack. And I think that maybe in the Vega experiments, we could have a drop flask, which is kind of like a couple of, how should we put this? A couple of Krypton 85 containing, what should we say? Car headlamps, and release the gas. And lightning is a thing that occurs around people trying to produce plutonium more often than it does in other places because of the Krypton 85. So that being aside, like I say, you can buy this commercially. I think I don't know which presentation it was, but let's go back to, and I'm going to see if you're actually saying anything. So I'm going to go back to this, which I've now translated, and I did this a little bit before I came. Yes, David, that's what I'm saying. Smash a Krypton car headlamp inside a Vega chamber. That's exactly what I'm saying. So, you know, rather than going to this gas supplier and saying, look, I'd really like to buy a canister of your radioactive Krypton 85. No, just go and buy a headlamp. Not all headlamps would have this, but that's you know, something to consider. Okay, so this translation here, you can see low threshold microwave ball discharge. Okay. And by the way, David, you don't need a lot of gas. I mean, we're ideally looking at very low pressures. So look at the pressures discussed here, 3 torr to 110 torr, and they mostly used 70 torr. Now, let's look at this. It's low threshold microwave ball lightning discharge. Now, when I first saw this, I thought these spirals were something that was being left by the actual ball lightning flying through the air. I hadn't clocked on to the fact that the ball lightning could actually locate and be fixed into place. But of course, we've settled that debate by the Vega experiments. We know that you can get these ball discharges and they will lock themselves. And they will lock themselves in one of two places. And this is the sketch that I drew of the kind of reactor designs that I'm going to discuss tonight, hopefully, if we can get to there. And I drew this almost within a few hours of seeing that video. And essentially, the ball lightning can attach to itself by the coherent matter boundary like that. So the ball is on top of the wire. Or it can attach so that the ball is going through, the wire is going all the way through to the other side. And it gets attached in the boundary on the other side. And that's what we observed in those experiments, the Vega experiments with the tungsten wire and also with the nickel foil in a coil. And you can see here that it will cut either here or it will cut here. It won't cut in both places to the best of my knowledge, but it'll cut there or it'll cut there. And it's just whichever yields first. Now, so on revisiting this, oh, you're not seeing the sketch. Oh, it was in the small little window. Am I not broadcasting that? Yeah, I'm in the little window. Let me show it. I'll go bigger. Here we go. Right. So here's my crummy sketch, and this is my radiation remediation nuclear reactor designs. And sometimes you can see how I think. So anyway, you've got that. So if we go down here, so. This is a piece of wire with the plasmoid on it, the ball lightning on it. And you've got the coherent matter zones, the so-called double layers. But I think the actual coherent matter mostly occurs right on the inside. The very, very inside is where it's most intense and there's a fall off. Okay, and then there's almost nothing inside. But anyway, so it cuts either there or there, and you can have a ball lightning that is attached with its coherent matter on this point, or you can have it so that it's attached on, get the orientation right, on the other side. So it's within that zone on the other side there. And we've observed that in the tungsten wire and the nickel foil coils in the Vega reactor. Okay, so did you see that? Okay, so I have some other paper here, and I even brought some pens with me. And if you have any ideas, okay, so I'm going to go back to what it says on that slide there. Okay, so obtained by testing special initiators in circularly polarized microwave radiation. Now, I am telling you that it occurred to me that you need circular polarization when I first started. I think it was the beginning of 2017. Anyway, I did similar drawings about the importance of circular polarization in microwave interaction of light, and I subsequently found that John Hutchison was circularly polarizing his light as well. Now, if you think about it, it's creating a spin. So that's kind of my logic. It was to have some spin going on in the light. And maybe that helps with interaction in more locations than where you would actually get if you would just, how should we put this? if you were just looking at resonant nodes in a resonant cavity. Okay, so this was obtained by testing special initiators in circularly polarized microwave radiation at 70 torr air pressure method of 70 torr air pressure. Now, the lower the pressure, the more likelihood, it makes it easier to create ionization. I've discussed other ways that you can increase ionization by adding Krypton 85 or something similar. But from my point of view, Krypton 85 is the one nuclei that's probably going to be best at doing this. Now, the microwave radiation, you can use different ways to ionize. You can use glow discharge, you can use spark discharge, you can use microwave radiation, or you can use radioactive isotopes. So the Krypton 85 above the plutonium production reactor is ionizing the air, and that's why you get more lightning over a production facility. So just having the Krypton 85 in the reactor will make it easier to create the coherent matter. Okay, so so then it's got short, powerful microwave pulse, and then a continuous emission with a, whatever that is, it might just be a bad translation from Russian, of 100 milliwatts per centimeter. So there's really not a lot of power. The helix structure is yes, we have tried the helix. In fact, that is why we had a coil, and in fact we had suggested other helix structures based on this slide coming out of an anode. But anyway, we're looking and finding other ways. The crack between the brass plates and the resonant cavity is a bit, in my view, it's allowing electron bunching, and I'll come on to that, and probably I'll do some sketches and talk through electron bunching and how that leads to coherence. But anyway, field of application 3 to 210 torr with few tens to few hundred. With a few tens to a few hundred milliwatts per centimeters. So we're really not looking at a lot of power here. And then 5 simultaneous ball lightning discharges were obtained at electrically coupled initiators. And so you can see the 5 ball lightnings occurring on each of the tops of these metal coils. Now, I would suggest to you that these metal coils are in fact the anode and there is a cathode somewhere. And so the ionized gas is guided to the tip, and the tip is the one that's presenting itself at the minimum distance to the cathode, and that allows for the focusing of the electrons at that point. That leads to electron bunching, which leads to coherence, which leads to the formation of the ball lightning, which likes to be fed by more electrons. Okay, you get it? Right, so that's where we are with this thing. Now, if you keep driving that, and you keep driving that, and you keep driving that, then you get to a point where that little coherent zone, that double layer, gets to a point where its energy level or its resonance is at the level at which it can do one of two things. One, actually probably many things, but let's just suggest two. One is that it prevents or removes the ability of the lattice bonds in the metal, because the metal's covered with plasmons. It's covered with free electrons. That's why when you take your electrical charger for your phone and you plug it into the bottom of the phone, you've got metal and it contacts the metal. They both have free electrons. That is the basis of the way that the electricity is conducted. Now, the Evo wants the electrons, so it can grab those away. So where they're going to come from? Over a certain point, it wants the electrons so bad. It wants it so bad that it will remove all of the electrons. Now, if you are a very large nucleus, like, I don't know, let's think of one, tungsten. If you're a very large nucleus like tungsten and you remove all of the electrons, well, the only electrons left are the electrons in the nucleus. Okay. And also, the electrons, are they holding the whole thing together? Well, I would guide you to the presentation by Leonid Roitskev from also the SWIFTBIC 2018 Ball Lightning and Cold Nuclear Transmutation Conference. It's on the MFMP channel. But in there, he cites 3 scientific papers. I believe they're published in journals. And what he is saying in reference to them is that there are isotopes that, and these are generally heavy isotopes, that are very heavy. And if you remove all of their electrons, that is to say, to completely ionize those nuclei, they fall apart. They fall apart. Now, if they're unstable already, and they have a natural unstable nature, and you remove the electrons, those ones are more likely to decay than the ones that are not unstable in the nucleus. They can survive longer. Now, what do you think is one of the most stable nuclei that exists? Any guesses? Any guesses? It's iron. It's iron. You could have a situation where you could use iron filaments or nickel. Nickels are pretty stable, but iron, you know, it's got a lot of stable nuclei in it, really stable nuclei. And you have the iron, and the iron is where you are getting your ball lightning forming, be it on the coil, like you see here in this slide, or be it in just a straight wire. And rather than it disappearing, like I have shown you for so many different examples, whether it was Mizuno, where he had his tungsten blow up, whether it was David Hudson, where he had a thumb-sized electrode disappear, whether it was what we've observed with the Mars gas, which we know has atomic hydrogen in it, and it's transmuted into elements, and that has ripped the material apart. And you see these same explosions that are partially under the surface that you also saw in the scanning electron microscopes from Matsumoto, from Mizuno. And it's not just that. Irving Langmuir observed this in the 1910s. In the 1910s. With tungsten. Okay? So tungsten is obviously, we know from our own research, from things that I've actually witnessed, that you witnessed with me live, right? Yeah, was it live? I think it was live, or very, very close to being live, the Mars gas. With that video and with other work by other authors, and also in the Sapphire reactor, that if you have the ball lightning at sufficient energy level or resonance with the tungsten nucleus, such that it can rip the electrons off, the tungsten nucleus will fall apart. The bits that don't like to be stuck to it will fall off. And so you basically have this disappearing tungsten, okay? So that makes a very good fuel, but it's not really that practical, is it? If you can get iron, if iron is able to, and obviously the great thing about iron is it is magnetic. Now, exotic vacuum objects are in magnetic and electrical or charged, or they're just magnetic. they're always magnetic. And so if you have iron, which is ferromagnetic, and it's as basically ferromagnetic as anything can be, it's ferro, that is a good focal point. So you'll have things that you can play all together to focus the process onto a zone. Now, I don't know if you can see it, and probably I'm going to draw this with a different camera, but before I get onto that, I want to go and look at a macro composite image that I have taken of the what do you call it? The brass plate, which I have here. This is on the table here. So this brass plate with the valley on it, and I'm going to see if I can pull up a really nice image of that and then move around it. Let's see if we can do that. So before I do that, there's something else I want to show you. Oh yeah, I can actually show you the Let's talk about reactor design. So I can actually talk about this here. Maybe I could actually just draw it on here. I don't know. Maybe I can just go to a blank page here. Can that allow me to do colour? Colour. Let's do. Ooh, hello. Right. Let me go there. We'll copy him. Oh, no, I didn't want to do that. Okay, that's my ugly mugshot. Right. So, what you can see, maybe, or maybe you can't see, in this slide here is the thing that I was talking about earlier is this. Ooh. And I'm saying that I've got 3 balls here. That's a terrible one, that last one. We'll get rid of that one. Okay, there's 3 balls, and I've got the wire going through it. So let me get a different color for our wire. And so what I was describing is that what I've drawn there is the double layer, and the wire goes to the inside of that, or it goes to the outside of the other one. And this is the wire as it's going all the way through. So that's what I was talking about earlier. And it basically can cut there or there. And that's what we observed on those experiments in the Vega reactor. Now, I've got 2 reactor designs drawn on this slide, which maybe are not very obvious to people. You can see there that I'm saying that probably we want iron or nickel as our wire for our ball lightning. Okay, and if I chose a different color, it would make more sense for our ball lightning here. There we go. What I'm also saying is I have a little reactor design here, and I'm going to see if I can draw that a little bit better on this slide here. Okay, so what I'm essentially arguing is that at the very least you need your rod, which is here. Let's see, is it going to draw me? Is it going to let me draw? Oh no, it doesn't let me draw on that. Wow, no, that's not very good, is it? Oh, well, that's disappointing. Okay, well, yeah, let me see if I can do it like this. What if I go there? Sorry, I'm still learning. Okay, let me see if I can draw it on this area. Is it going to let me draw? No, why doesn't it let me draw? Oh, I've got no line thickness. Is it? I don't know. Oh dear. Right, I'm going to maybe go to physical paper here, because this is just not working for me. I'll go there and cancel that. Okay, you can look at that whilst I set up another camera. Okay, let me just see if you've got any comments here. I don't think yours are any more illegible than mine. Study that image for a minute. I'm gonna, because I actually do want to talk through the not Matsumoto, the other visual here. So I want to look at this, and I want to look at this, and let me see what happens if I go open there. Oh, great. Okay, just hold it a little while. I'm going to see if I can actually bring this. Oh no, that's going to be even harder. Oh no. I just want to be able to zoom around it easily. And what do I have? Right, will this let me zoom in? No. Oh, okay, I've got a solution here. Control, okay. Ah, okay, I found a solution, so it's not all the end of the world. Let me see if I can cut here and just create something here. Talk amongst yourselves. Oh, okay, this is what I wanted. Okay. So what I've done here is I have produced a macro image by taking a lot of photos and stitching them together. Now, I haven't done depth of field, and actually I'm going to pause this work because I'm hoping there's a fantastic guy out there that has suggested he may be able to help get something that I can use to produce much higher and much more depth of field, much quicker than the process I'm currently using. And it doesn't seem to be worth my time to be doing that now when I can process a lot of samples very quickly and produce a lot of high quality videos for you. So anyway, we're going to look at this, and this is a rather high resolution image of the valley. And firstly, I just want to draw your attention to this, which is what I call the Anc. So up here you have your ball, like this is where the ball lightning was, and you have your two branches, the little knot here, and the outflow or the inflow, depending on which way you see it. And I think that's rather lovely. But and you will see a lot of different things here, so you will recognize some of these features that we've looked at in much higher resolution, and I will go and look at those images too with you in a minute, maybe. But what I wanted to draw your attention to is this pattern of that is presenting itself all over the place. It's quite distinct here. Now, whilst, and I will talk about this in other presentations, whilst this area here, this it's catching up with me, yes. Whilst this area here is brass, and maybe I can draw on it there. Choose a colour that's actually going to be seen. This area here. This area here. Oh no, it's moving that. Oh God. Oh dear. Sorry. Let's lock that. Okay, should be better now. Whilst this area here, this whole area here is essentially looks like it's brass, although it's a different colour. And it has this texture over this kind of like I think it's called dromedaries or something like that. It's kind of like these shapes of mounds that you get after a glacier has come down and carved out the land. It's kind of like these shapes. You also saw this on the scanning electron microscopy of the Hutchison fracture sample. And so that's actually what's going on that whole area there. But that is not what I really want to draw your attention to. I want to draw your attention to this. So basically this brass is not, it's eaten away. There's a curve in it, as we saw when we looked at the Vega Valley edge, but it ostensibly is brass. And hopefully next week or the week after I can get this under a large table SEM and we'll be able to know whether that really is just brass. But you have this very strong boundary here. Let me go right into that. This very strong boundary, okay? And then you have these other boundaries here. Now, are these just oxidation states? If they are just oxidation states, it doesn't necessarily mean that nothing interesting was going on, because there was only residual oxygen in this reactor. And a lot of the other, you can imagine that this should be hot. So why is there not all oxidation everywhere here? Why has the bulk of this not become copper 2 oxide or copper 1 oxide or whatever? Anyway, these could actually be oxidation states. Now, the oxygen potentially could actually be coming from an alpha conjugate of carbon. Why do I say that? Was it Takaaki Matsumoto and before him Yul Brown? Yul Brown found that if he took radioactive material like Cobalt 60 or americium 241 and he mixed it with aluminium. The aluminium is very good at providing electrons. It's a low melting point, but it's also it's a single isotope. It's 27. Its nucleus has a fairly high NMR moment, and so it can interact with EVOs in good ways. And then he put iron filings in there, and I described this in my Russian presentation, that the iron provides the anchor on which the EVOs that are forming build, that come out of the HHO gas. And then at a threshold point, which is the the Curie temperature of iron, the EVOs all fly off, they organize into a big ball lightning, transmute everything and go poof in a big flash. So I've given the science behind the observation that he observed many, many times and was demonstrated to politicians in the US in the 1992, I think it was. And what he found is that, and it's in his patent actually, if you go and look at Rex Research, you'll see this. The product that he gets mostly is carbon. And this is exactly what Takaaki Matsumoto said in Fusion Technology in 2001. And he says, basically, the ring clusters, the product, what doesn't matter what you put in, whether it's light elements or heavy elements, what you mostly get out is carbon. Now, I've described why I believe it's carbon. Carbon is the first conjugate of alpha particles, i.e. 2 protons and 2 neutrons. That is not helium. And it can't be rubidium, it can't be beryllium, because beryllium-8 is not stable. It decays almost immediately to helium particles. So the first stable solid, and obviously it's high temperature, but the first stable solid alpha conjugate nuclei is carbon. The next one is oxygen. So if this is just oxygen oxides in this area, it could actually just be oxygen that's synthesized from ripping the lead apart, or ripping the copper, or ripping the tin, or ripping the zinc apart that's in the brass. But I suspect that this dark area you're seeing around here will be carbon. And why do I say that? Well, I say that because if we go and look where these ball lightning lived, they lived in the crack. They lived in the crack, and they were semi-regularly spaced. You got some real messed up stuff going on here in this area here, okay? But here there would have been one. Here there would have been one. Here maybe. Here there would have been one. There might have been one here even. There might have been one here. You know, they're like, but they don't like each other too much to come together unless they're overstimulated, and then they wet into each other, as it said in that 2001 fusion research paper that was published in Japan. Here's another one. Now, what you see in these center areas, are these what I call kernels, but they're blacker and more black than any other area. And also, actually, as you see, you go down here, you've almost got a meandering. You've got like an outside here and an inside here. And you can imagine that the process was going on, that this started off with an excited macro itonic cluster, a ball lightning here, a plasmoid, this ball of fire. And it's throwing out things as it's getting excited, and it's bouncing around here, and it's bouncing around here. So what you've got is a channel, a macro channel that was bored by the large structure that spread out, and maybe even spread the whole thing here. But then at another phase in the experiment, a smaller one came down here and it bounced, and it left this black trail. Is it oxidation states of copper? I don't know. I think it's likely to be carbon deposits. It's going to be fascinating. You see it here, like something's come out of here. It's hit this corner here. Then it's come over here. It's spun round here. It's hit here and it's come down here. Again, it's flooded over this area and it's come down here. This is so beautiful. There's so much rich information that you can see in this. And it's not happened just once. It's not just happened here. It's happened over here. And it's happened over here. And it's happened over here. And everywhere you look, this same pattern is repeating. The brassy look, the yellow look with the hard, dark, maybe carbon or a type of oxide on the boundary, and then the fade off. The inside of the self-organized plasmoid structure is basically untouched, other than the material that's eaten away. And as I've said to you before in other presentations, if it's diamagnetic, it's not going to want to be touched. You know, if you wanted to make a spaceship from this, you would make it with bismuth, right? Because it's the most diamagnetic material by far. And you'd want to coat it with a whole skin of plasmoids, or you'd want to trap the plasmoids between something that has a different level of diamagnetism. Anyway, that's an aside. So you can see how these plasmoids have travelled down here. Now over here you see one where there isn't really a channel. It's just come out and it's left the carbon here, and it obviously got to an extent. Here it just comes out and then it almost doesn't have an end. It kind of dissipates out here. So it's just beautiful. It's just beautiful. So beautiful. So beautiful. And then obviously you've got the miniature ones. And when I do a proper depth of field on these channels, you'll see these in much greater depth. Okay. Gert, what track were they following? I think they are traveling along initially. You know, as it's growing out, it's kind of, it's finding a weak point in the structure and it's traveling in that direction. However, when the whole thing is energized, you know, when the whole thing is energized, then it might be that it's out here and it's out here and it's out here at the same time, and they're holding their position. They're holding their position, just like lightning does. You have an ionized gas channel and it moves down it and then it holds it. So what Ken Shoulders says is that all lightning, whether it's going from ground to cloud, cloud to ground, or cloud to cloud, depending on the potential differences, it first starts with the ball lightning, and the ball lightning comes down and it ionizes the channel, and then it will flash and discharge through that channel. So the channel exists and you don't see it, but there's a massive ionized or an affected path through which multiple discharges can go. And that's what you see when you super slow down lightning. It's not just one continuous discharge, it's like a pulse of series of discharges. This is less Lichtenberg style, because Lichtenberg is it's kind of more like tree fern like, whereas this is a self-organizing magnetic fluid, in my view, and I will go into much more detail hopefully next week on that. Yeah, they've got their own magnetic fields, and that's just what I was saying in this, you know, this slide I have here. If we cut to that, it'll come to there in a minute, maybe. What I'm saying in this slide, you can actually see I have a ball in the top left-hand corner, and you can see I've written north here and north there, and what I've actually got there, if I get rid of those two and make a much smaller pen. This was our loop, okay, of wire in the coil in the Vega experiments, and we've got one ball lightning here and one ball lightning here, and this has its north there, and that's got its north there, and then there's the south here and the south here. Okay, so they're self-organizing even in that respect, orientating themselves to the wire, and that's why, you know, it's cutting maybe here at those points. Okay, anyway, so where you can go back, you can rewind Gert and look on double time and catch up, or you can look at it after the presentation, or my rambling is over. This is not so much of a presentation as a rambling. But anyway, like I say, I've got so much to get out, and I just want to give you guys some ideas to start thinking about. Okay, so maybe I can take a different image here and show you. So I did a focus stack on the magnetic particle that you saw in the last video. And what is it? What am I doing? Photos. There we go. Is it going to open in photos? Yeah. So this is a photo stack on that magnetic particle. So it'd be interesting to see what this particular thing is. Can you see that? Are you seeing it? I'm not actually showing that, am I? And it's not actually changed. Why is it not changed? Okay. Oh, there we go. I actually have to ask it to look at it again. Okay. That's a bit weird. So this is this. Obviously coppery. It looks like it's been born in that same place. You can see these paisleys going on here. So much smaller paisleys, and this is a symbol of this technology also, and I will describe it at a later time. In my view, what's going on. And let me find that I've got quite a few images I want to share with you that tell a story. Okay. What is going on? Okay. Okay. So first up, let me have a look at this. Yeah, let's have a look at that one. I've got to find a better way to do this. Because that goes there, but it doesn't come to here. I have to change it. Oh dear, what's the time? I've got another half an hour. Oh, now it's giving me two photos. Okay, here we go. Okay, so can you see that? So this structure here, and I will go into a lot of detail about how I see these forming, but you can see this very strong demarcation line at the bottom here with these dromedaries, or I can't remember the name. It's a sort of term when you're looking at glacial effects. But they're lumps, but they look more like the brass, although you can actually see what the brass looks like there. This is actually brass color. So, you know, maybe something's changed on the surface here, or it's a change in the metal constituents, like maybe the more zinc is left. What I found actually was in the brass coin, if you remember from the Amasa gas exposure, that zinc doesn't get affected, and there are, in my view, reasons for that, because whilst copper is diamagnetic, there's a issue, there's NMR with the nucleus and so on. But anyway, so you get reasons why the zinc gets left behind. So I think this is a higher proportion of zinc in here, and this is the actual brass that's ordinarily there. And there's some very wonderful things that you can see here. Firstly, if this is copper oxides are melting at a much higher temperature. And the interesting thing is you've got a ball here, and you've got two holes with this liquefied. It's like it's not balled up or crystallized or whatever this is over here. something, a ball lightning has gone in there and it's actually turned this to a fluid in its view there. Now, the distance between these two, I've actually got a shot. Now, maybe I can actually just run around in this. Maybe I can just, will it allow me to look at different images? Can I go, maybe I have to zoom out and then go, oh, there we go. So this is a close-up on, oh, okay. So this is some broken material here. And actually, the reason I'm showing you this one is because this area over here is close to the where the actual ball lightning sat for a very long time. And I believe that either this may be copper black, it's like a real one type of copper oxide, but I believe that there will be a high degree of carbon on this. So I'm really interested to finding out whether that's actually the case. Then you can see that it's actually kind of like a skin, and then you've got these the crystals here, these what I call the kernels. And actually what's happened here is this is a big section of kernel that's just broken and shifted over to one side. And actually what I want to do with this new camera technology, I should be able to get 2 centimeters close to it, but be able to see the full depth of field without being effectively in contact with it. What I've been using to take these images is using this device, which is a Narugo microscope lens, and I attach that onto the back of this Samsung S7, which is a nice 1.4 micrometer pixel sensor, 12 megapixel camera, and I can then push that forward and backward to get this fixed focal length, change its focal position, and that allows me to take a focus stack, and then I put the focus stack in Photoshop, and I can end up with seeing a bit of depth of field here. What you're seeing here on the right side of the image here is what I believe is contacted to the actual ball lightning itself, and then you're looking into part of the channel there. So let me see if I can go through and see other images here. Okay, so that's the one we see. Oh, okay, so this is the valley meander, and this is a meander through. And again, I think if I had this with focus stacking, you would see, with more focus stacking rather, you would see the colors made sense for smaller ball lightnings traveling down the channel. What you're seeing here is the ring light. So what the Narugo does is it takes the light from the camera and it channels it through into a ring light around the lens. So it's right there, and that produces these rings around these highly specular or reflective surfaces. So these might actually be pure copper or something else, I don't know. But what you can see is that even in the structure of these things, there's even more structure. So for instance, if you look here, there's some kernels here, but on the surface of the kernels, you've got a regular ordered array of other structures, and they actually appear to be almost in pairs. You know, there's one side and one the other side, and they are facing like an arrow away from the main plasmoid. It's absolutely incredible what you are looking at here. It boggles the mind, the level of self-organization and the wheels within wheels, the as above so below that's going on here. It's just phenomenal. So you can see it over here. In these kernels, in the kernel, they have substructures which are organized. So yeah, it's just breathtaking, Okay, so I have to zoom out. Okay, and then maybe I can go to the next one. Now this is what I call the Eastern Plateau. So if you go up, how do I do this? Okay, so what I'm looking at here. Let me precisely get this, is what you're going to see in this next video, in this next image, is this section here. So I don't know if you can see where my mouse is. I'm going to draw around it, actually. We're going to be looking at this area here, and I took four sections, and I did focus stacking on that to see what's coming out here. So you've got this plasmoid that's coming over here. You've got our what do you call it? Our Anc there, and you've got some plasmoid that's come down here, but the section we're going to look at is this one here. So I'm going to cancel that, and I will zoom out of this. And is it going to let me do that? I'm going to get this at some point. Oh, it might just be big images. It's just wait. They are very big images, by the way. It might just be waiting to catch up. Okay, so this is the Valley East Plateau, as I'm calling it. And you can see how, for instance, here, you've got a plasmoid that's come in, and it's kind of like hit maybe come in at this angle, and it's just hit the level here, and it's just sent out fragments, and they've created this wetted sloshing, and then you've got this aftermath of all of the material that was eaten out of here. Like it's absolutely stunning. It's such an honor to be able to look at this stuff. Okay, so you can see how it can interact with material here. You've got this one, which I rather like, up here, and you've basically got the. This is almost an exact equivalent of the structure that you see in Bogdanovich's paper, where they observed these things traveling around for 2 days after the experiment was over. So I'm going to cancel. So you've got a spiral structure there, and that's actually quite large. Anyway, there's lots going on in that. So let me see if what else I've got here. Is it going to catch up with me again? Okay, so here you can see the top of the channel is 1.142 millimeters. The bottom of the channel is less, and you can imagine that there's a shape of the plasma, self-organized plasma in there is making this channel. Again, this is focus stacked, but this is using the dyno light, so it's less detailed. And so what I'm trying to focus on is to spend more time getting the right tools to do this properly once than kind of do a half-assed kind of approach to it. Right. So is it going to let me do this? Come on. Can I do it like that? Okay. I don't know. Oh, is it going to let me slide? No. I'm sorry. I'm still struggling to work out what am I at the bottom of the page? That might be the problem. Yes, I'm at the bottom of the page. So I'm going to go up. It's going to take a bit of time. Yes, Corky, there are melted stone tracks like that in the Giza pyramid. I didn't know about Peru, but in Giza. And it's between the sandstone blocks, or whatever they are. And they've got what appears to be granite, melted granite in between the sandstone blocks. So, but I think we'll know what we're talking about soon. So we're back to this channel here. Okay, so yeah, this is a close up, and you can really get to see the kernels here. Okay, I'm going to stop, and I'm just going to quickly sketch out what I have on my reactor designs, because I've not got to where I've got to go, and there's a kicker slide at the end that I want to give you. And Happy New Year for anyone who knows anyone who's from Asia, because it is Asian New Year. Okay. Why isn't it going to show? Maybe I need to go like that. I'm just going to drag this one into a different frame. And then you can see the very basic effect of the plasmoid Okay. I'm going to have to be very quick. And I will do 3D diagrams of what I'm talking about. So let me get a pen, a portable scribe. Okay, and that and that. Okay. Let me see if I can. I've got 5 minutes to make you a reactor. Okay, so let me get a different camera in play here so we can see what I'm talking about. Let me see if I can show this. Is that working? Is that plugged in? Maybe. Cameras. Okay. Is that going to work? I don't know. Oh, I don't know. Cut. Right, I've got a camera here. Okay. Right, it's gonna be very weird. I don't know if you can see that. Let's see which way's up. That. Yeah, no, where's my working area? Oh dear, it's all the wrong way around. That's gonna be upside down for you as well. That's not good. Okay, just give me a sec. Who knew drawing on a piece of paper would be so hard? Okay, so we want this one. I'm going to okay. Okay, so I'll go back to this one for the minute whilst I'm getting the other camera up. Maybe I can use a pen. What I'm going to be quickly talking about is this rough design up here. Okay, and essentially what I've got is I've got a wire and I have our ball lightning on top, and to achieve that we want our cathode above, and that's our cathode, and our anode is this one. Okay, and what we have is a ceramic, let's say call it a ceramic plate underneath. Okay, and the wire goes through that ceramic plate, and it has a hole that's just big enough to put the wire through. It doesn't need to be massive like that one. And the plate vibrates, and what it does is our fuel combination, which could be our, I don't know, cesium-137, our strontium-90, whatever, our waste products, or just tungsten powder or something. We have that coming down, and it hops down, and what we're trying to do is we're trying to hop into our coherent matter area, and the coherent matter area will be at the resonant or energy level required to destroy this matter. And the matter might be a mix of fuels where you get one like maybe tungsten powder and then the material that you want to shred apart, and you are using the energy that's released from the one heavy nuclei falling apart and all of the atomic components and subatomic components that potentially coming from that electronuclear collapse to remediate the nuclear waste. So let me see if I can do a better job on my drawing here. So I can do that, and I can do vertically flip source. Is it going to work? I don't know. Okay. If I go, let's try this. If I go up, no, that's the wrong way. I'm going to need to horizontally flip source. Up, down, left, right. Good, excellent. Okay, let's see if this works. Oh dear. Okay. So, what I'm saying is, this is going to work. I have a little hole, and through that hole, I have a wire. Now, the wire could be a straight piece of wire that's fed. Let me get the focus right on that. Let me get the focus. What's the focus? Autofocus. Let's try that. Is it right? No. It's no good. There we go. This might work. So this is our wire. Now we could have wire that comes off a spool and gets fed through our ceramic plate hole. Okay. And our ball of fire with its boundary layer is attached on top like that. And we have an array of these things. Okay, with our wire coming through and our balls of fire on top. Okay, and this vibrates up and down. Okay, could be ultrasonically done, and our fuel particles are bouncing up and down, up and down, up and down, up and into the coherent matter area here. So it gives them like the maximum. So for instance, if you got our coherent sphere here and we've got blah blah blah, our thing hops and it spends as long as possible going through this area. Okay, and the idea is that there is a resonance or an energy level that doesn't damage our ion probe here, right? But is sufficient to disassemble the matter that's being bounced through. And on top of it, you have your cathode. If I can show you that there, the cathode. And effectively, each one of these is an anode. Now, you're going to have gas-produced transmutation gases. Yeah, you might want your 85 Krypton in here to accentuate the thing. You'll probably want some nitrogen and you'll want some hydrogen in there. And I would suggest probably some small amount of H2O. Because the oxygen, I believe, is playing a role. So that's kind of like one type of reactor. And in this kind of like more advanced version of it, if you can see that, this one, which is the one that I drew. Effectively, you have a screw feed of material from a huge hopper. Would I get that in view? So you have a huge material feed and that dumps it down here and you have some riffles like you have on a gold collection thing, and they bounce up here and they get caught in the riffles and they get bounced over in a loop that's over here, and then they hit the top plate and they go along and they do their transmutation with our ball lightning here and they come off and they fall down here, and you might have a magnetic trap here or something, but it just goes round in a loop. And so forth until you've dealt with your heat and your radioactivity, and it in theory should produce a lot of heat. It probably produces a very large amount of strange radiation, and then you need to use material suitable for capturing that and thermalizing that and making that place safe. So that's roughly the schematic of it. And so I had that idea. I drew these drawing the night or the day or within 24 hours of seeing that particular experiment, and I'm going to go back and I'm going to show you something which I think you might find quite interesting. Yeah, if I could. And then I need to go. Okay, so what I want to show you is something. Let me get rid of these. And I go here. Okay. Open with. So in a few days, I hope to be in the possession of, when people that think they want to control these things, the book of Takaaki Matsumoto's work from 1989 to 2000 and, well, 2000, but I think it was assembled in 2001. And I am going to go and try and go here and okay. Before it was sent to me, and just in case, I asked Sho to take a bunch of photos. Now, I don't know if this is clear to you, but I had this idea. In fact, you can go and look at ECAT World, and I said, I've got a generalized idea for how to make a thing that will remediate nuclear waste and produce heat. At the same time, I've got another piece of paper that looks to direct electricity. And what I didn't do today is talk about electron bunching, but very, very simply in the work of Solin from 92, he has his low vapor pressure, high melting point metal. He has an electron beam coming into it. It melts a area. You get a melted area and a non-melted area, and you get electron bunching. The electron bunching leads to coherence. In Takaaki Matsumoto's, one of the last presentations I did, he uses a linear accelerator to cause electron bunching to stimulate the production of itons, these combinations in his mind of positrons, electrons, and neutrinos that form this mesh-like structure that covers the material that then goes to do the electron-nuclear collapse or electronuclear regeneration. But if you look at this, and here, from 1996, now bearing in mind that Matsumoto's main job, it turns out, for much of his career was to find ways to deal with nuclear radioactive waste. And look at this number 62 here. T. Matsumoto, 1996. Sprayer for radioactivity incineration with tiny ball lightning. No one's had an original idea in their life. No one's had an original idea. And there's one more. So I'm interested to see what these actually are. Maybe I can just go to it. No, it's just not going to let me, is it? And then I must go. Okay. I need to change this again. No, did the other one. What? No, it's not showing me, is it? I'm going to be in trouble now. Come on. There we go. Oh. Okay, I don't know if you can see this, but nuclear regenerated products during discharges with wire electrodes. Comments to electronuclear reactions. This is 1999 sort of area. Nuclear transmutation, incineration, collapse and regeneration by an electrical method. This was presented in the proceedings of the 18th meeting of the Japan Society of Energy and Resources, Tokyo, 1999. A proposal of direct nuclear incineration of spent fuels. Proceedings of the spring meeting of Japan Atomic Energy Society, Hiroshima. Electronuclear reactions in micro ball lightning. What I am saying to you, essentially, is that I think that we have a method. We have shown over the last several months and over the last 3 years a step-by-step learning process and physical evidence, and maybe this and more clean versions and more precise versions and replicated versions of this will lead us to a situation where we know what it's doing, we know the sphere of influence that it's occurring over, and we know the part of the ball lightning that does the job, and we can rip matter apart, we can encourage unpleasant nuclear material to become stable and edible. And this, for me, is one of the things that I set out to do a couple of years back, 2018, basically from the beginning of 2017, when I realized that the most easy thing that you can do with this is to tear matter apart, and on a more subtle level, to cause an unstable thing to become stable. And that, I think, has direct applications, and a combination of those things, as I discussed in this presentation, could lead to massive net energy generation from not just radioactive fuels, but also other nuclei that are readily available to us to use as fuels. So thank you very, very much for your time. It's time for me to go. So I'm going to say goodbye, and I will see you in the next time, I guess. Thank you very much.